Hello students, hope you are doing well. I am Dr. Mitali Pal, Assistant Professor of Chemistry from University of Science and Technology, Meghalaya. In this video, I am going to discuss coordination chemistry. This is a very important topic for BSc and MSc chemistry as well as crucial for competitive exams such as NET, GATE or SLET. Okay, so let us start. Now, Swiss chemist Alfred Werner is known as the father of the coordination chemistry. So, you can see his image here. He proposed the theory in the year 1893, even before the discovery of electron. He received Nobel Prize in 1913 for his work. Okay, so according to Albert Cotton, another famous scientist, Werner's theory of coordination chemistry is probably the greatest conceptual contribution to inorganic chemistry. Now, let us first discuss what Werner's theory is. In this, in a series of compounds of cobalt chloride with ammonia, he found that some of the chloride ions could be precipitated as silver chloride on adding excess silver nitrate solution in cold, but some remained in solution. What does it mean? Okay, so what he observed that when he is mixing 6 moles of ammonia with 1 mole of cobalt chloride, then a yellow colored compound is formed. When 5 mole of ammonia mixed with cobalt chloride, he observed a purple color compound formed, and when he mixed 4 mole of ammonia with 1 mole of cobalt chloride, he observed again two colored products. One is green and also in violet. So this was very surprising observation for him. Then he further checked what it is formed. To check it more further, he added excess amount of silver nitrate solution to each of the compounds, and after the adding silver chloride solution, he observed white precipitate of silver chloride for all of these experiments. But when he measured the amount of silver chloride and he calculated the moles, then he observed that when he added 6 mole of ammonia with 1 mole of cobalt chloride, there he got 3 moles of silver chloride precipitate. When he used 5 moles of ammonia, he observed 2 moles of silver chloride, and when he used 4 moles of ammonia, then he observed 1 mole of silver chloride is precipitated. This observation triggered him to think him in a different way, and he proposed the following postulates of the coordination theory. Okay, so he propounded this theory in the year 1898. Okay. Now, what are the points we will discuss one by one and also explain what it means. So, the first one is that in coordination compounds, metals show 2 types of linkages or valences, primary and secondary. Now, this is one typical picture and geometry structure of coordination compound. Okay, so so here you can see the cobalt, the metal transition metal cobalt is coordinated with 4 ammonia ligand and 2 chloride ligand in the coordinations with the coordination bond, and another chloride is there outside the coordination sphere, and that is having ionic interaction with the cobalt ion. Okay, so Now, what does it mean by primary valency and secondary valency? Okay, we will discuss this one, but together with that one we will also discuss the secondary valency and primary valency. So these points number 2 and 3 also I will first tell here, then we will discuss. The second point, it tells the primary valencies are normally ionizable and are satisfied by negative ions. Okay, so here in this complex you can see that ammonia is a neutral molecule, but chloride is a anionic ligand. It is a anion. Chlorides are anions. Okay, so it is telling that primary valencies are normally satisfied by negative ions. The secondary valencies are non-ionizable. These are satisfied by neutral molecules or negative ions. So neutral molecule like ammonia as well as negative ion as chlorides, both is used to satisfy the secondary valency of a coordination complex. Secondary valency is equal to the coordination number and is fixed for a metal. Okay. Now let us understand these points with an example. Okay. So this is the example of a coordination complex. Now let us find out primary and secondary valencies for this compound. Okay. So to find out the primary valency of the compound, coordination compound, we have to first find out what is the charge of the central metal ion. Okay, the charge on the central metal ion itself is the primary valency of that metal. Okay, now how to find out the charge on the metal ion? So to find out the charge on the metal ion, we have to find out how many negative ligands or anions are coordinated with the metal ion. Okay, so in this complex we can see that cobalt is ligated with two chloride ions. Chloride ions are negative ions, anions, and ammonia are neutral molecule, so it is not an anion. So obviously the charge of the whole complex will be balanced, so the charge will be contributed by the negative ions. So here we see that as a whole this coordination complex is having a charge +1 outside its coordination sphere, and that is balanced by this chloride ion outside. Okay, but this plus charge obviously is charge of the metal ion. Okay, now what will be the charge total charge on the cobalt? If we consider the charge of the metal ion, we don't know, so we can take it as X. Then we can take the charges of two chloride ions. So there are two chloride ions, but both is having -1 charge because it is an anion, 1 anion, and they are having -1 charge. So -1 into 2, that is total -2, equals to, it will be the whole charge on the complex. So this charge is coming due to contribution of negative anions and the metal ion, charge on metal ion. So if you do addition subtraction, finally you will get the charge +1. So the total charge is +1. We don't know the charge on the cobalt, that is X, and we know the charge on the chloride ions, that is -2 total because of two ligands. So the charge on the cation will be X equals to +3. Okay, because it is a simple calculation, you can see. So the charge on the metal ion is +3. Therefore, the primary valency of the cobalt ion here is +3. Okay, so we can see the primary valencies are satisfied by negative ions, right? So you can see negative ions are having role to satisfy the primary valencies. Okay, but there is no role of the neutral ligands, ammonia, to no role for finding out the primary valency. Okay, now I hope you understood what is primary valency. Now let us go to understand what is secondary valency. Now secondary valency is satisfied by both neutral molecules and negative ions. So here cobalt is having bond, coordinate covalent bond with ammonia, 4 ammonia ligands, 4 neutral ammonia ligands and 2 chloride ions. Okay, now the number of coordinate covalent bond made by the cobalt ion with its ligand will determine the secondary valency. So if the central metal ion makes 4 bond, then coordination number will be 4. If it makes 5 bond, it will be 5, and if it makes 6 bond, so the coordination number will be 6. Now we can see in this example, cobalt is making 6 bond with 6 ligands. So 6 ligands could be either neutral or negative or positive, but it is finally making 6 coordinate covalent bond with the metals ligands. Okay, so that means the secondary valency of this complex is 6. Okay, so I hope you understood this one also with this example, which is primary valency and which is secondary valency. That means in a coordination compound, the metals will always show 2 types of valencies, primary and secondary. So primary valencies will be satisfied by negative ions, in this case chloride ions, and secondary valencies are generally not ionizable and they will be satisfied by both neutral and anionic ligands which are directly attached by covalent coordinate bond with the metal ion. And why they are not ionizable? Because they are making covalent bond. So this bond will not easily break when you dissolve this complex in water. Okay, because they are covalent bond, they are not ionic bonds. So they will not be dissolved in polar solvent. So those you will not get as a separate ion when you are dissolving this complex in water solvent. Okay, so that's why they are not ionizable. So in this total compound, these 2 chlorides are not ionizable as they are bonded with a covalent bond with the cobalt metal. But this chloride which is outside of the coordination sphere, which is having in ionic interaction with the metal, that can be ionized easily and you can get this as an ion. So this chloride is ionizable, but these 2 chlorides are not ionizable. Okay. Now let us go to the 4th point, which says that ions or groups bound by the secondary linkages to the metal have characteristic spatial arrangement corresponding to different coordination numbers. So now let us understand this point. So this word spatial arrangements, what does this mean? Spatial arrangements, this means that how ligands are arranged in different directions in space. Okay, because metal is in the center, so there are ligands, but they are bonded with the metal ion in a particular direction because these are making covalent bond with the metal. That covalent, and how covalent bond is made? By overlap of orbital. So first overlap of the orbitals happen, then electron sharing happens, and then covalent bond forms. Now when a coordination complex is formed, the metal orbital will overlap with the ligand orbital having lone pair of electron, and then lone pair of electron of the ligand will be shared by both. So vacant orbital of cobalt will overlap with the field orbital of the ligand, and then both electrons will be shared by both metal and the ligand, and then covalent bond will form, and this is a covalent coordinate bond because the electrons is only given by the ligand. Electron pair is only given by the ligand, so it is actually a coordinate bond or dative bond. It is a one type of covalent bond. Okay. Now, so you understood what is spatial arrangement, because orbitals will overlap in a particular direction, because as you know that px orbital, py orbital, pz orbital, there are three orbitals inside the p orbital, and they are given the name as px, py, pz. Why? Because their electrons are in one particular direction. In this three-dimensional axis, px, in case of px, we know that p orbitals are dumbbell shape. So in case of px, electron density is in the x axis, in the direction of x axis. So there is no electron in y or z axis. Okay, and py is having electron density. So this is electron field electron. So this is the electron density in the y axis, and this is having in z axis. And similarly, when we have d orbitals, because metal will involve their d orbitals for bonding. Okay, p and d both. So dxz, dyz, dz square, x square, y square, dxy and dz square, all these are given this axis name xz or yz. Why? Because this case also the electrons are distributed in particular direction of your three-dimensional space. Okay, so when this orbital of the metal will overlap with the metal ligand orbitals, then the bond will form in a particular direction. So if px is making bond with the ligand orbital, if px orbital of the metal will overlap, then bond will form in x direction. If py overlaps, bond will form in y direction. If pz orbital overlaps, then it will form, bond will form in the z direction. That's why bonds in a coordination complex like this one will form in a particular direction, x, y, z or x, y, y, z. Okay, so in these directions this will form. So that's why if bonds are forming, maintaining a particular direction, then obviously there will be arrangement of ligands will make a particular geometry. Okay, they will attain a particular geometry after all bonds are formed. So when there is 6 ligands, normally they attain the geometry which is called octahedral. Okay, so all the ligands are in x-axis. If we consider this one is x-axis, so both ammonia in x-axis, this both ammonia in y-axis, and these two chloride ligands are in z-axis. Okay, so that means they are making a particular three-dimensional structure or geometry. Okay, and that is actually called spatial arrangements. So ligands will have, okay, a particular spatial arrangement. And see, the ions which are bound by secondary linkages, means which are satisfying the secondary valency, means which are making directly covalent bond with the ligands, so they will be making a particular arrangement. The ligand which is outside of the coordination sphere, that is not involved in the coordination bond, so that will not, because this chloride which is outside of this coordination complex, that will not have any spatial, that will not make any spatial distribution or geometry, because this is having ionic interaction with the cobalt, and ionic interaction have no direction. Okay, because this is a ion, this is a ion, like NaCl is a ionic compound, so there is no direction, it is not direction dependent, because ionic bonds are not direction dependent, but covalent bonds are direction dependent, because ionic bonds don't need overlap of orbitals. So there is no fixed particular direction where the ionic bond will form. Okay, that's why this is having no particular direction where this cobalt chloride interaction is there. Okay, I think you have understood now this point, the fourth point, that ions or groups which is bound by secondary linkages, which is actually satisfying the secondary valency of the metal ion, have characteristic spatial arrangements corresponding to different coordination numbers. Obviously, if coordination number differs, then the geometry will differ. If you have 6 coordination bond like this complex, then the geometry will be octahedral. But if you have 4 coordination number, then the geometry can be square planar or tetrahedral, most of the cases. Okay. Now metal ion will have the tendency to satisfy both of its valency, primary valency as well as secondary valency. Okay, and metal ion commonly exists as positive ion. Okay, so now I have discussed all the postulates of this coordination theory. I have tried to explain the postulates of coordination chemistry with all the basic necessary explanations. So this is the first video on coordination chemistry, ends here, and next video will continue with IUPAC nomenclature of coordination complexes. Thank you.